So this is the presentation that some of you are expecting with all. So I will go through the objectives of this work. It was focused on the food and feed production at industrial level. And from the objectives of the work, then we have 4 outputs that I will go into more detail. So the main objective of the work was to demonstrate the feasibility to produce at industrial scale in a sustainable and affordable way 4 main outputs. The microalgae biomass that was mainly dried, the protein isolates from these microalgae, also innovative foods with the microalgae and the innovative feeds. So now entering the first output, the industrial cultivation and the drying of the microalgae. To achieve this cultivation, we got the inputs of the work that Iago presented already. We also got inputs from the sustainability assessment that we'll presented later today. And we basically, the producers that were Necton and all microalgae, produced 4 different strains of algae. And then we dried the algae to provide the dried biomass for the industrial production of foods and feeds. The drying was also with the input of the work that was presented by IMA. In parallel, we also did the protein isolates, or a task that was led by Alexandre. The initial plan was to use these protein isolates for the foods, but as we already discussed, the costs and the low yields then led us to the conclusion that we would not do this industrial scale production of food with protein isolates. So the microalgae cultivation, we use different reactors. At Necton, we focus our production in photobioreactors, tubular photobioreactors. And for this project, we cultivated Nanochloropsis and Tetraselmis. You already heard about this algae. In all microalgae, the focus was the production of chlorella, the different kind of chlorellas in fermenters. And we also did there in all microalgae the production of spirulina in raceway ponds. Then the drying. For Nanochloropsis, we selected freeze drying, although, as Ima presented, the solar drying was a good option, a very nice option. Then for industrial scale, it was not yet well established at the company, so we moved on with the standard procedure at Necton, that is to freeze dry. For the chlorellas, all microalgae has industrial spray drying, so that's the way they did to dry the biomass. And for spirulina, we did mainly solar drying. Just a brief conclusion of this first part of the work, just to show you the biomasses that we gave to the rest of the partners. For algal source, for the protein isolates, we did mainly paste, in this case, Tetraselmis paste and spirulina paste. For the foods and feeds, we provided dried biomass. So you have here the amounts. For the foods was mainly all microalgae, providing spirulina and chlorellas. For the feeds, we produced Nanochloropsis and all microalgae, smooth chlorella. So the scale-up to industrial level of the production of protein isolates, as I said, was not fully achieved due to the low yields and high cost, but we tried. We had the frozen microalgae, Tetraselmis and spirulina, and with the inputs from what Ima presented, we tried to do the protein isolates at industrial scale. I will not go into much detail, but this is the process flow diagram for the extraction of soluble proteins of Tetraselmis and spirulina. the steps are very similar. There are some differences between the two strains. There is a thawing. In spirulina, there is also a maceration and the addition of additives. This step is basically to burst the cells, so we release the contents that they have inside. Then we have a centrifugation step to separate these contents that are in the water from the pellet, let's call it in the end, it's an insoluble green residue that you can valorize later. In the water, we have the crude protein extract. That is what we use to move on. For tetracelmis, we move directly to ultrafiltration to remove salts, small protein sugars, basically to clean it. In the spirulina, we do two steps. We have a microfiltration for clarification and then the ultrafiltration. And with this, we get the protein isolate. And I believe Ima already showed this slide. So tetracelmis, as you heard, has a very low yield of protein extraction. We could only achieve 3%. And even so, this protein isolate was not pure. It only had 27% of proteins. So tetracelmis is not a good option to move on. Spirulina, it was nice. It provided a yield of 31%. If we look to phycocyanin, that is one of the main pigments in spirulina, and it has a commercial interest. It was around 80% of yield of extraction of phycocyanin, so it was quite good. And here the protein isolate is quite pure, with almost 80% of proteins. Conclusions about this part of the work. Not all the microalgae strains are suitable for a sustainable and solvent-free protein isolate at industrial scale, as Ima already said. If we go to the isolation of molecules or proteins, we have to know that this, of course, will add a cost to the product. This cost has to be justified by an increased value of the isolates. Maybe if they have a higher functionality, it gives value to it. Or isolation of other valuable compounds, for instance, omega-3 fatty acids, or as Ima also said, the valorization of the side streams. Now, entering the food formulation at industrial scale. We had the dried microalgae, mainly were the algae that are food approved, chlorella and spirulina, and with the input of the work presented just before me, we made the food products. We have this that you already heard about, and then they were used for consumer tests. I will not speak here about consumer tests. This will be talked about afterwards. So just briefly to show you the prototypes that the industrial partners did. So Gutarra did a protein source vegetable cream with 1.5% of spirulina. They did it at industrial scale, a lot of Tetra Paks that were then provided for the consumer testing. Enervit did two kind of products, shake drinks and sports bars. The shake with 5% smooth chlorella. These ones went for consumer testing. They also did sports bars with 5% spirulina, but these products were then not chosen for consumer testing. Calais did grisinis and toasts. Grisinis are breadsticks with 3.5% smooth chlorella. They provided several bags with around 20 pieces each for the consumer testing. They also did small toasts with 1.5% spirulina, also for consumer testing. Alver did the carrot ginger soup with 5% honey chlorella for the consumer testing. Tradizione Padane did vegan fresh stuffed pasta with 3% smooth chlorella. And Viva Maris, together with Dill, did vegan meat sausages with 3% golden chlorella. In this case, because they are vegan, no animal gut was used for the coating. And it's a product that has a short lifetime, shelf life. So it was a bit of a logistic issue that the partners for the consumer testing had to deal with, so that they could have all the products together to do consumer testing. So, as I said, I will not present the results of the consumer testings. My colleagues will present it later. And what we can say here is that the innovative food formulations were successfully produced at large scale by the industrial partners. Now, about the feeds, I will show some results. So, what is the work? What was the work plan? So we had the dried microalgae, nanochloropsis, and chlorella, and we used them to make the feeds, and then the feeds were used to make the in vivo trials, and then we also did meat quality tests. For the feeds, we again got the input from previous work, and we produced, as you already heard about, feeds for 4 groups of animals: poultry, swine, fish, and shrimps. We did in vivo trials in all those, and the meat quality tests will be done in all except the shrimps. I will not go into detail of this table, just to tell you what Nutrition Sciences did for the piglet trial. So they have a control feed, normal feed, and then they did 3 replacements of crude protein from soya with different amounts of nanochloropsis. And what these numbers tell us is that basically there is no significant differences between the feeds. So nanochloropsis is a good replacement of soya protein. About the poultry, it was not the case. So here, IRTA did a feed with 30% of soya protein replaced by nanochloropsis. What they observed was a reduced growth at the later stages of the trial. They also observed a changed skin and breast color, that there was a tendency for yellowness. But on the other hand, there were no changes in the quality parameters of the meat. But in overall, we can say that nanochloropsis here is not a good replacement for soya. About the fish, the trials were done by Vitafort. They also did the feeds. So we had 3 kinds of feeds: a control and 2 experimental. The first one with 10% microalgae inclusion, the second with 20%. And depending on the fish that they used a different algae. So for the common carp, they used nanochloropsis. For the African catfish, they used chlorella. And these are the results. Basically, no difference in both cases. So in overall, nanochloropsis or chlorella is a good replacement of soya. We also did meat quality assessment, and again, no differences between the treatments. So once more, a good replacement of soya. About the shrimps, the trial and the feeds were done by INVE. 2 inclusion ratios, 10 and 20% of nanochloropsis. The first trial failed, so it's now being repeated, and because of that, the results are only expected in the next few weeks. Here you can see the larval stages of the shrimp, so you can have some nightmares today. And these are the conclusions of the innovative feeds, but I will finish also with a general conclusion. Nanochloropsis is a good replacement of soya in piglet feed and in carp feed, as chlorella is in catfish feed. But nanochloropsis is not a good replacement of soya in poultry feed. There is still some work to do. The sensory evaluation of meats and the shrimp trial is ongoing. And in overall, although most results are good, as we already discussed, price-wise, we are still a bit far to be able to compete with soy. It's a completely different market, and microalgae are still expensive because we are an industry that is quite new. Agriculture has hundreds of years. Microalgae has a few dozens. So we are still, and we hope to reach there. And I want to thank all the partners for this wonderful work in this project. And I'm now waiting for your questions.
Any questions? Okay.
Hi, thanks for a really interesting presentation. Do you know or understand or have an idea about why it doesn't work for poultry, but it does work for the other organisms? So the fish and the...
Not totally sure. Might have to do with digestibility that we already spoke about, but maybe Gert Josep can give an input there.
Yes, maybe digestibility. That's one aspect. On the other hand, what we saw at the start of the trial, at the poultry trial, it worked. It was only at the end of the poultry trial that something happened. Now there's a huge difference between a swine and a chicken. I mean, a chicken is mainly based on texture and color. That's why chicken is attracted, while a piglet is more on taste. So most probably also the organoleptic characteristics were different. So we did not explore further. But in terms of digestibility, that's clear. We did some digestibility trials, and the digestibility was lower compared to soy. So what's the reason? We don't know yet. Yeah. But there was a clear difference in digestibility trials between the two animal species, as well as in the physiology of the animal. Yeah. Thank you.
On this topic of digestibility, Nanochlorops has a strong cell wall. Did you break the cell wall before?
No, that actually was one of my comments
Okay.
that I forgot to mention. Yeah, we are in disadvantage. We are comparing crude protein of soy that is there, the protein, with a cell that is closed and has Nanochloropsis, as you said, a tough cell wall. So, yeah, in the next project we should tackle this question. Massimo.
Thanks. An issue that keeps coming up in the presentations and the discussions is comparing the low price of soy with the higher price of the algal inputs. And I wanted to ask a question because obviously it's frustrating to hear that because we know that the soya is doing all kinds of damage, to the Amazon, et cetera, and it's being transported halfway across the world. So that's problematic in a moment when climate change is such a massive issue. Conversely, algae could avoid those costs. And I guess if we drew the circle a little larger, something that we could look at would be how, production of microalgae to replace soy could be a recipient of climate mitigation money. It seems like that would be something that'd be very worthwhile exploring because it's a question of the different revenue streams you're gathering. And, a ton of carbon is I think it's 100 euros now. It's a lot of money. And the reality is that you'd be avoiding these very damaging things. And the only reason why it's cheaper is because those are externalities that are being ignored by the market. But that could be addressed. That's what I'm trying to say.
That's a wonderful point, yeah. We don't say that soy should be taxed for the deforestation, of course, because then it would increase the price of the food of the people. But the thing of the carbon and how can we help to expand the production of microalgae? At this moment, we are very small and we are competing or trying to compete directly with a huge business. We cannot give the jump to that level. So maybe we need to go step by step. And one is to receive money from entities because we are more sustainable, not to tax the others.
To outcompete the others with the additional revenue streams.
Yeah. Thank you.
No more questions? Okay.
Thank you. Thank you for the presentation, really inspiring work. In the beginning of the presentation, you mentioned something about production of protein isolates not being economically feasible. And so do you think the opportunity to make it economically feasible lies in the downstream processing, optimization of the downstream processing, or in the optimization of the fermentation itself, kind of optimizing the yields, reducing energy costs, or would you go to genetically modified organisms? And have you done something in this regard?
So I'm picking some words of Ima that we already discussed something related to that question. First, thank you very much for the question, a very important one. It has different factors. Yes, if we reduce the cost of the microalgae production, it will then reduce the cost of the protein isolate. But there is still a lot of work to do with the protein isolate production, with the extraction of the proteins, test new methodologies or invent new methodologies. So there is still a lot of work possible to reduce all the costs since the beginning, the cultivation, until the production of the protein isolate. So that's why the main reason we are still far from the price of the soya protein in the market. Thank you.